2.2, the derivatives of polynomial functions. The constant function rule. If f at x equals k, where this k value is some constant, then the derivative of f at x, so f prime at x, equals 0. In Leibniz notation, it's d by dx of k, right? Like that would be the function in there, equals 0. So example 1, what is the derivative of f at x equals 5? Well, f prime at x equals 0 because 5 is a constant. Now, what is the derivative of y equals pi by 2? Well, pi by 2, we know that's radians. It's a radian measurement for 90 degrees. So if we want to do, we can either do y prime equals 0, but a better way for the notation to do this, because this is written in y, we're going to do dy by dx equals 0. Now, the power rule. A power function is a function in this form. So it's f at x equals, it's some number to the exponent n, or some x value to the exponent n, where n is a real number. Okay, so that means that there's the number in the exponent. We could talk about like x squared, we could talk about x cubed, x to the 4, whatever it is, and so on. Okay, we can even talk about x to the 1/2. Any number, anytime when n is a real number in the exponent, that is going to be the power rule. So if f at x equals x to the n, where n is a real number, then the derivative, what's going to happen is we're going to bring this number n down in front and multiply n by x, okay, or n by the coefficient, okay, and then we're going to subtract 1 from the power. In Leibniz notation, it's going to look d by dx of x to the n equals nx n minus 1, or to the n minus 1. So determine the derivative of the following, and there's a couple here. So f at x equals x to the 7. So we're going to do f prime at x. What happens is this 7 comes in front, so it's going to be 7x, and then instead of writing 7 in the exponent, we're going to subtract 1. So f prime at x is going to equal 7x to the exponent 6. Okay, b, f at x equals 1 over x cubed. So this doesn't look like a power rule, but if we rewrite 1 over x cubed, we know in order to get this x cubed to the numerator, it's actually going to be x to the negative 3. Right? Don't forget the exponent law that if we have a over b and it's raised to the exponent negative 1, what ends up happening is we have to, in order for us to raise this to a positive exponent, so like positive 1, we have to flip this number in here, b over a. Okay, so in this case, we're just going backwards, and one of our numbers is just a 1. So to bring anything from the denominator up to the numerator, we're then going to express it with an exponent of a negative exponent. So now that we're working with f at x equals x to the negative 3, in order to find the derivative, what we're going to do is we're going to bring down this exponent into like where the coefficient is. So we have negative 3, and then we're going to have x, and then negative 3 minus 1. Whatever that exponent is, minus 1. So our derivative altogether is negative 3x squared. Sorry, negative 4. I think I did 3 minus 1 instead of negative 3 minus 1. Okay, next one. S equals t to the exponent 3 over 2. So I'm going to call this one ds by dt because we are differentiating s with respect to t. I'm going to bring this 3/2 in front of the t, and then I'm going to take the 3/2 and subtract 1 from it in the exponent. So I get ds by dt equals 3/2 t to the 1/2. So now d by dx of x. So this is asking for the derivative of x. So we can say d by dx of x equals, because that's just the notation from like up here. Here's the thing. So if we have x is actually naturally to the exponent 1. So I'm going to bring down that 1 in front of the x, and then in the exponent, I'm going to go 1 minus 1. So d by dx of x equals the coefficient of 1, you don't really have to write, so I'm going to write x to the exponent 0. Okay, but we know anything to the exponent 0 is going to be the constant 1. So d by dx of x equals 1. A constant multiple rule. If f at x equals k, g at x, so if there's some value k that's in front of some function, and k is a constant, then when we solve for the derivative of f at x, what we can do is we can essentially pull the k out and just multiply it by g at x, or g prime at x, or the derivative of g at x, whatever you want to call it. Okay, so the f prime at x equals k g prime at x. And in Leibniz notation, if we're doing d by dx of ky, then this equals k, because we're basically pulling the k in front and leaving it as a constant, and then we're going to find the derivative dy by dx. Okay, so determine the derivative of the following. So f at x equals 7x cubed. So when I'm doing this, I am going to look at this as 7 being my constant times x cubed. So what I'm going to do is I'm going to look at this as 7, and then I'm going to find the derivative d by dy, or sorry, d by dx of x cubed. Okay, so this is the function that I'm going to do. So f prime at x equals 7 times, and then for the x cubed, I'm going to bring down the 3x, and then it's going to be 3 minus 1, which is squared. So f prime at x is going to be, all we do is simplify this. 7 times 3 is 21. X squared can't simplify. It's 21x squared. Okay, B, f at x equals 12x to the exponent 4/3. So what this actually means is we're dealing with f at x equals the constant 12 times the power function x to the 4/3. So what we're doing here is we're going to bring down the 12, nothing's happening to it, and we're going to find d by dx of x to the 4/3. So f at x equals, keep the 12, times. This 4/3 is going to come down in front of the x. So we have 4/3x. Then in the exponent, we are going to subtract 1. So at the side of my paper, 4/3 minus 1, which is 3/3, we're going to get 1/3. So altogether, f prime at x equals, if we do 12 times 4, we get 48. Divided by 3, we get 16. Okay, so these two numbers we multiplied, and then we write x to the 1 over 3. Now the sum rule and the difference rule. So the sum rule, if functions p at x and q at x are differentiable, aka we can find the derivative of them, and f at x equals p at x plus q at x, okay, then what ends up happening is f prime at x, so the derivative of f is just going to be the derivative of p plus the derivative of q. So it's just a sum of its parts. And we saw this for the limits as well. So in Leibniz notation, d by dx of f at x equals, so the derivative of f at x equals d by dx of p at x plus d by dx of q at x. And the difference rule is very similar to the sum rule. It's just with subtraction. So again, if functions p at x and q at x are differentiable, and f at x is the difference between these two functions, then the derivative of f at x equals the derivative of p at x minus the derivative of q at x. And in other words, in Leibniz notation, rewritten here as well. Okay, so differentiate the following functions. F at x equals 3x squared minus 5 root x. So what we're going to do for this one is f prime at x, we're going to find the derivative of 3x squared. Okay, so this 2 goes to the front, and it is 3 times 2x. And then we're going to subtract 1 out of the exponent. 2 minus 1 gives us 1. And then minus, so I'm going to do minus 5, 5 being the constant, so that's not going to affect the derivative of root x. And I'm going to rewrite root x up here as x to the 1/2. So just kind of like on the side of the paper so we can do some work. So we can bring that 1/2 down in front of the x, which goes here, write x, and then subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. Okay, now we simplify. So f prime at x equals 3 times 2, which is 6. X to the 1 is just x. So the derivative of 3x squared is just 6x. And then for the difference rule, we go minus, okay, so 5 times 1/2, it's still going to be 5/2. And I'm going to leave it as a fraction. I'm going to show you why. Okay, when we're dealing with x to the negative 1/2, in order to deal with x to the negative 1/2, we usually like to fully simplify, we have to write the negative 1/2 because it's an exponent. We have to write it as a positive. So in this term, this x to the negative 1/2 is going to come to the denominator. So it's going to come where the 2 is, and it's going to be written to the 1/2. And this is the fully simplified version. If you remember from yesterday's note when we did this the long way with limits, if we have root x, which is x to the 1/2, the derivative, so d by dx of x to the 1/2 is 1 over 2 root 2, or sorry, 2 root x, or in other words, 1 over 2 x to the 1/2, either one of these. Okay, y equals 3x plus 2 squared. So let's go ahead and expand this. 3x plus 2 times 3x plus 2. Okay, and we're going to go, this is going to be 9x squared. 3x times 2 is 6x. 2 times 3x is 6x. And 2 times 2 is 4. So what we're actually differentiating is 9x squared plus 12x plus 4. Okay, so what we're actually differentiating is, so dy by dx is going to be d by dx of 9x squared, and then d by dx of 12x, and then d by dx of the constant 4. Okay, so dy by dx equals, so first let's differentiate this, 9x squared. We're going to bring the 2 down, and as a short form, I'm no longer going to write 2 times 9. I'm just going to do 2 times 9. So I'm going to write 18, and then x squared, the squared becomes x to the 1. Okay, so the derivative of 9x squared is just 18x. Now, the derivative of 12x, so plus, right, the rule for sums, yep, the sum rule. Okay, so 12x, that's naturally to the exponent 1. If I brought this 1 down, well, 12 times 1 is just 12, so let's just leave the 12 there. And then 1 minus 1 is 0. Well, we know, side of the paper, anything to the 0 is just 1, so the derivative of 12x is just 12. Okay, and the derivative of the constant 4 is just 0. That goes to 0. So we're actually done. The derivative of this entire equation here, 12x squared plus 12x plus 4, is 18x plus 12. Example 5, determine the equation of the tangent to the graph of f at x equals negative x cubed plus 3x squared minus 2 at x equals 1. Okay, let's do that first. So if we have, and I'm just going to rewrite f at x equals negative x cubed plus 3x squared minus 2. What we're going to do is we are going to find the derivative of f at x. And how we're going to do that is we're going to find the derivative of each of its parts. Okay, so for negative x cubed, this is actually negative 1x cubed. So let's bring down the 3 to times with negative 1. We get negative 3. And we're going to subtract 1 from the exponent, x squared. Then we're going to go plus, we're going to do derivative of the second term here. So we're going to bring down the 2. So 2 times 3 is 6. And then x to the 2 minus 1 is just going to be x, right? Like x to the 1. And then the derivative of the constant is nothing. So this is our derivative. Okay, so we can say f prime at 1, which is what our question is asking us, right? We want to find the derivative at specifically this value. Okay, we can just go ahead and sub in the 1. So we get negative 3 times 1 squared, which is negative 3, plus 6 times 1, which is 6. So f prime at 1 is just 3. And this is all for answer A. So we know that the slope of the tangent line is at 1 is 3, but we need the full equation of the tangent. So what we need is we need a point x comma y. So we're going to take this 1 and we're going to sub it back into the original. So we're thinking to ourselves, okay, what is f at 1? Well, negative 1 cubed plus 3, 1 squared minus 2. Negative 1 plus 3 minus 2. We get 0. So we get the point 1 comma 0 to use as our x and y. And f prime at 1 is 3, which is our m value. So we can go ahead and go y equals mx plus b. The y is 0, the m is 3, the x is 1 plus b. So y equals 3 plus b. We can bring the 3 over, and we get b equals -3. So the equation of our tangent line at x equals 1, and we can write that if you want. So the equation of the tangent line at x equals 1 is y equals 3x minus 3. So now determine the points on the graph where the tangents are horizontal. So if we had some graph, and just going up to the original here, okay, I don't know exactly what this looks like, but I know it's cubic, and we have a coefficient of with negative. So we know that it's going to go down, up, down. It's going to go from quadrant 2 to quadrant 4, okay, and it's going to be cubic like this. So what ends up happening is this is going to play a very, very large role in our course, okay, where the tangents are horizontal. So that would be when there's this turnaround point, okay? So the tangents would be vertical or like on a slant here, and they would round out. And right when there was that turnaround point, the slope is going to be 0. And then they're going to go up again. And then again at this turnaround point, the slope is going to be 0, and then the tangents go on forever. So what we want to know is we want to know when f, go back to my blue, okay, f prime at x equals 0. When this occurs, the tangents are horizontal. Okay, in other words, when negative 3x squared plus 6x equals 0, the tangents are horizontal. So in order to solve for this, negative 3x squared plus 6x, I'm going to factor out, just common factor, negative 3x out of each of these terms. And we get negative 3x bracket x minus 2 equals 0. And we're going to get the x values, x equals 0 and x equals 2. So there are going to be 2 occasions where the tangents are horizontal, and that's when x equals 0 and x equals 2. B specifically asks us for the points. So in order to find the points, we're determining x comma y. So all we want to do is we want to go to the original, sub in 0. So negative 0 cubed plus 3 times 0 squared minus 2. And then we're going to sub in 2 as well, again to the original. F at 2 equals negative 2 cubed plus 3 times 2 squared minus 2. Okay, so f at 0 is, that goes to 0, that goes to 0, and negative 2. So our 1 point is 0 comma negative 2. And f at 2 is going to be negative 2 cubed is 8 plus 2 squared is 4. That's 12 minus 2. F at 2 is going to equal 2. So 2 comma 2. So we can say, therefore, the tangents are horizontal at 0 comma negative 2 and 2 comma 2.